Good evening. Today's session we start a new chapter, Thermodynamics. In the previous chapter we studied about the thermal properties of matter, and in this chapter we are going to study about the laws that govern thermal energy. Thermodynamics is a branch of physics that deals with the concepts of heat and work and also the interconversion of heat into different forms of energy. So, as we proceed or as we start this chapter, it's important for you to know what you mean by an adiabatic wall and a diathermic wall. So, that's what we'll discuss first. So, an adiabatic wall is a insulating wall which does not allow heat transfer. For example, if you have two systems, for example, we have two gases, A and B. We have two systems, two containers with two gases at different temperatures, but they are separated by an adiabatic wall. Now, as I told you, an adiabatic wall is an insulating wall that does not allow any heat transfer. So, no heat is allowed to be transferred between the two systems A and B because it is separated by an adiabatic wall. On the other hand, if you have a diathermic wall, what we call as a diathermic wall, and if these two systems are now separated by a diathermic wall is a conducting wall. It allows heat transfer. So if this wall is a diathermic wall, it allows heat transfer, and therefore heat will be transferred from the gas if this is at a higher temperature to a gas if this is at a lower temperature till the two of them are in thermal equilibrium. This word thermal equilibrium means they are having the same temperature, or all bodies or systems that are thermal equilibrium have a common property called temperature. Temperature is the same for all bodies in thermal equilibrium. So you may define temperature as that property of a system which determines whether it is in thermal equilibrium with other bodies, whether or not it is in thermal equilibrium with other bodies. So now that you know what is thermal equilibrium, we can move into the Zeroth Law of Thermodynamics. So that's what we are going to deal with now. Zeroth Law of Thermodynamics. Zeroth Law of Thermodynamics. Now here again, we have three systems, A, B and C. Our system, we refer to a gas inside a container. So we have here a wall here between A and B, and this happens to be an adiabatic wall, which means it's an insulating wall. No heat transfer is allowed between A and B. We have a diathermic wall here, which is a conducting wall. It allows heat transfer, separating A and B from a common system C. So we have A, B and C, which are three systems, let's say gas in different containers, but A and C are connected by a diathermic wall, so is B and C, but A and B are separated by an adiabatic wall. So even if A and B are at different temperatures and no heat is allowed to be transferred between A and B, A and C, there will be heat transfer because it is separated by a diathermic wall, and so it will transfer heat till A and C are in thermal equilibrium, which means they will have the same temperature. Similarly, B and C also are separated by a diathermic wall. So there will be heat transfer between B and C till B and C are in thermal equilibrium, which means these two will have the same temperature. That means A and B must be in thermal equilibrium. So Zeroth Law of Thermodynamics states that if we have two systems which are in thermal equilibrium with a third system separately, then these two systems are in thermal equilibrium with each other. So that is very simple, Zeroth Law of Thermodynamics. After this, we go on to discuss about heat and internal energy, how they are different. Heat and internal energy of a system. Okay? Heat and internal energy of a system. Internal energy of a system is denoted by the letter U. Now, internal energy of a system is a state variable, meaning state variable like pressure, volume, temperature of a gas are all state variables. It means that pressure, temperature, volume and internal energy depends only on the state of the system at that moment, not on the path taken to reach that state. So internal energy, that is why we call it a state variable. So depending on the state of the system, that means the pressure, the volume and the temperature of the system, the molecules of the gas, if our system is a gas in a container, the molecules of the gas will have, they're all in vibration. They'll have kinetic energy and potential energy. The sum of the kinetic energy and the potential energy of the molecules of the gas enclosed inside a container, or the molecules of a gas that forms the system, is what you call as the internal energy of the system. So if you increase the temperature, the molecules start vibrating faster. They have larger kinetic energies. You will be increasing their internal energy. Same way if you cool it, I'm just giving an example, the internal energy decreases. Now we go on to look at the two ways in which we can change the internal energy of a system. Suppose we have a gas, let's say we have a gas enclosed inside a cylinder and it is fitted with a piston. We have the gas enclosed inside the cylinder, fitted with a piston, and this piston is a movable piston. Okay, so this is our system with what we are talking about. And if you want to change the internal energy of the system, that is the gas, there are two ways in which you can do that. You can bring, the first method is, you can bring this cylinder in contact with another body at a higher temperature than the gas, so that when you bring it, suppose you keep it at with a body at higher temperature than the gas. So naturally, some amount of heat will be transferred to the gas because it is at a lower temperature, and the heat transfer will continue. Let me call the heat transferred as delta Q. This heat transfer will continue till the gas and this body are in thermal equilibrium. Once they attain the same temperature, then no more heat transfer will take place. And as the heat is absorbed by the gas, the molecules of the gas start moving faster and they have larger kinetic energies, and therefore their internal energy will increase. So that is one way in which you can change the internal energy, by bringing it in contact with the body at a higher temperature. The other way around is also, that means you can bring it in contact with the body at a lower temperature, in which case the heat will be transferred from the gas to this body, and as the gas loses its temperature, or the heat is lost as the gas transfers heat to the body at a lower temperature, the internal energy of the gas will reduce. The other way of changing the internal energy is, let's say you push the piston down. Okay. Now if you push the piston down, what happens here is, you are increasing the pressure of the gas, and as you increase the pressure, the molecules will start vibrating faster, and you are increasing the internal energy of the gas. So another way of increasing the internal energy is by doing work on the gas, by pushing the piston down. So the two modes in which you can change the internal energy of a system is either by bringing it in contact with the body at a higher temperature, so that there is transfer of heat from the body at a higher temperature to the gas, thereby increasing the internal energy of the gas. Or by pushing the piston down, you're doing work on the gas, and as you do work on the gas, you're increasing the pressure, you're decreasing the volume, thereby increasing the pressure, and thereby increasing the internal energy of the system. So also if you push the piston up, the gas will expand, and as it expands, the pressure decreases and the internal energy of the gas decreases. So we are just discussing two ways in which you can change the internal energy of a system, either by heat transfer or by doing work. Now you might have noticed from this discussion that pressure, volume, temperature and internal energy are all state variables, which depends only on the state of the system. not the path taken to reach that state. Whereas heat and work are two modes of changing the internal energy or changing the state of that system. From here we go on to the first law of thermodynamics. First law of thermodynamics, which can mathematically be expressed as delta Q equal to delta U plus delta W, where if you again we go back to our system, which is a gas enclosed inside a cylinder with a movable piston. Now here, suppose this gas is brought in contact with a body at a higher temperature. We just discussed that there is heat transfer. Let delta Q be the heat transfer from the body at a higher temperature to the system, the gas, which is at a lower temperature. This quantity of heat absorbed by the gas is used up for two things. One, to increase the internal energy of the system. That means the molecules gain the heat and thereby increase its kinetic energy, and thereby increase the total sum of kinetic energy and potential energy is what we call as internal energy. So there is an increase in internal energy. Also, the gas expands, pushing the piston up because it is absorbing heat. The gas expands, pushing the piston up. So this gas is now doing work. It is doing work on the environment. So that is delta W. So first law of thermodynamics simply states that the quantity of heat absorbed by a gas or a system, part of it is used to increase its internal energy and the rest of it is used to do work on the environment. So here delta W. So suppose let's say our piston was initially here and it has been pushed up through a distance delta X, and let the piston, the base of the piston be a circular area, so that the volume increase delta V can be written as, if you take the volume of the cylinder, the base area of the piston is circular, and it has been pushed up through a displacement delta X. So the volume would be base area into height. So the change in volume would be the base area A into the displacement through which it has been pushed up. So you may give this as delta Q is equal to delta U plus work done. Let me show you. Work done we know is force into displacement. Now force, as you know, is pressure into area, because pressure is force by area, into displacement here is delta X. This A delta X is what we now call as the change in volume. So this is P into delta V. So you may also state first law of thermodynamics as delta Q equal to delta U plus P delta V, where delta Q is the quantity of heat transferred to the system, which is used up to change the internal energy of the system and also in order to change the volume, whereby there is work done by the system. Okay, so we will stop our discussion of the first part of our chapter now and continue in the next session. Thank you.